So I'm going to talk about scaling development with a thing that we call QEI, and I'll explain that weird acronym in a few minutes. So I work at LinkedIn. And hopefully I'm not talking from the bottom of a jar now. So 225 million users and growing fast. 500 plus developers, almost 600. A page like that takes effort of dozens of people and can take. Okay, the sound is still coming back. Okay. We are releasing our software to production about 3 times a day, 5 days a week, and we try to develop as fast as possible. We use trunk development model, which means that we don't have branches anymore. Everything goes to the same trunk. Trunk is either open, which happens about 99% of the time and growing, or it's closed because, well, something has happened. We automatically roll back the commit that broke the trunk. All is shiny, all is well, and some would say that it's just like in some stories from the past, everything is orchestrated, everything is smooth, everything goes really, really well all the time, right? Right? Yeah. So we don't actually orchestrate stuff just like in the Opera. Rather, we're trying to adopt a fast, vicious pace of development where we are running into each other and try to improvise our way out of collision every time. So if anything, I would rather use Thelonious Monk as the icon of our development rather than some symphonic orchestra. And when so many things are going so fast, the ideal metric that I would like to see happening is the total throughput of our engineering. Anybody have read the book The Goal by Ellie Goldratt? One person. That's it? Anybody read the book The Phoenix Project? Oh, better. So Phoenix starts where the goal has left. This is actually a picture from the Phoenix cover. And in the goal and in the Phoenix project, the idea is that by minimizing the queues that we have in front of our deliverables, we can get everybody much more productive, much more empowered, and much more autonomous in what they are doing. So I'm going to talk about autonomy. I'm going to talk about empowering people. I'm going to talk about finding what hinders the development speed and what we try to do to accelerate development, why it didn't work, what we did after that, why it does work, and why we're still not satisfied with what's working because we would like it to work much better. So I've been at LinkedIn for about 4 years. I still associate myself probably with C programming language more than with anything else, and whenever I have time, I compete on my bicycle. Doesn't leave me lots of time to compete on my bicycle, but agenda. So 2010. What did you do in 2010? I was working about 18 hours a day, every day, and we were basically trying to get LinkedIn to that coveted S1 filing. And we had to create a disaster recovery site. We had to increase our growth. We had to make sure that the site is not going down every now and then. We had to make sure that whenever we're releasing software, we do not stop the site once every 2 weeks for about an hour to actually release software. And it sucked. And the most painful manifestation of how badly it sucked was building software locally when I was going to add a new feature. Check this out. That's me ranting. And I didn't break any speed limits while driving. So the idea was that everybody had their own Mac tower, and everybody was deploying their own version of a stack on that Mac tower, full Java stack, a Mac tower, Mac Java. And we were deploying the stack from a branch, and we were hoping that nobody broke our branch. And we were developing our feature, and all was shiny, and then we were merging. And after a merge, things were going wild, because somebody has changed something, and we had no idea. So excuse me, I'm a little bit old like that, and I'm going to use UML, because I'm old like that. And the systematic problem that we saw is that we had about a few hundreds of developers. Each of them had a minified version of the full stack, which was supposed to be similar to the production, except that it was not at all. We were not running anything on Mac on production. We were running on Solaris. We were not putting everything into one box. We had a few dozens, and then a few hundred, and then a few thousand boxes. We didn't have zero latency on production. We also didn't have zero latency on Mac, but the latency on Mac was still much more consistent than latency on production. And the problem of that, the systematic problem of that, was that we were developing software for Mac, and then we were trying to ship it on Solaris. We were developing software on one box, and then we were trying to ship it to multiple boxes. So we had, in fact, two development cycles. One when we were writing the code, which worked, and then we were trying to implant code that was written on a single box into a distributed environment. No wonder it sucked. So the way it sucked has been actually presented really well by talks such as latency is the mind killer. When it takes you about 40 minutes to deploy something, it's killing the mind. And by the fact that by putting hundreds of services into a single box, we were running slow, we were running even slower with the debugger, and we had to become experts in maintaining stacks on our own machines in order to push something completely different to production. So we were becoming experts in the wrong direction. So our first approach to the problem was to say, we're not going to deploy everything. If, for example, I'm working on the homepage, I'm only going to deploy things that are required by the homepage. If tomorrow I will be working on the profile page, which is a different page, I will deploy different services. So we started to deploy only parts of the stack, which sped things considerably, but it introduced a new problem. We had to learn how to ignore errors. And we became really good at ignoring errors. Yeah. Yeah, good skill to develop, right? So to summarize, we lost flexibility because once we slimmed the stack down, we can't really use multiple pieces of software to create something new, so our innovation and productivity was decreased. We had to plan really carefully ahead, which is not the bebop that I was describing earlier. It's much more about, Ring of Nibelungs or what's not, 3-day opera that had to be planned ahead. Didn't work that well when we had still have plenty of competitors breathing up our neck. And we had to understand the local system really well, and then move to a production system which we didn't understand because we focused all of our power, all of our effort to understand the system that we didn't have to understand. Well, we said that this is not working. So we decided that instead of going through partial stacks, we'll start cramming more functionality into pieces that we call services, the war archives that we are deploying. And that way we would save the overhead of all the dependencies that we are putting into the wars, which worked really well. We saved quite a bit of memory. Everything was working much smoother. And again, we solved the wrong problem because now our development stack deviated from the production even further. So not only we had to move from from a single machine to multiple machines, but we also had to move from 3 services into 15, whereas we never tested it with 15. We only tested it with 3. Luckily, we were so frustrated that we decided to hack a little bit, and we decided to create a new Hack Day project. LinkedIn is a great place to be if you like to write code. And we have a Hack Day once a month where you can write anything you would like to, including including improving your Photoshop skills if that's what you would like to do. So we have created a Hack Day project. We called it a quick deploy, and the idea was that deployment should be quick. And what we've done is we took a bunch of machines, put them aside, deployed everything there, and hacked together a clever way, or so we thought, a clever way to route the topology between the local machine, where a person would deploy only a single service, which is fast, because machines were built to deploy hundreds, and everything that this person shouldn't be working on would be deployed remotely. Novel idea, almost like cloud, except that we were very non-inventive here, so we didn't use cloud. So the new system really made developers happy, except for one guy. That one guy, who was not made happy. So we hired a guy to maintain our shared boxes, and they were breaking constantly. Not only they were breaking constantly, now we had the pain of the changes that are not understood falling on the shoulders of a single guy. And he was doing a great job, but he was not a happy person, not at all. I wouldn't be either, not after the first 15 minutes. So, yeah, it was deploying quick. It wasn't operating quick, though, because we still had single boxes, crammed all of our stack into those single boxes. And now, instead of having a single developer working with a single box, we had 35 developers working on the same single box, which was slow in the first place. So we were deploying quickly. Operation was slow, though. And we didn't cover all use cases, because in order to make it solve, we cut a few corners, and then people had to deploy more and more and more stuff on their machines. So instead of moving into a model where we had single machine, single service, single debugger, we were sort of iterating back. However, it was a success. It was a great success because we understood that we are actually moving to a direction that's good, that can be improved. It was a potential. And then we came with that horrible, horrible, horrible acronym of QEI. It was to be QED, but apparently people don't understand QED, so we came with QEI. QEI stands for Quick and Easy Integration. And the idea was to get rid of all the shared stacks. Instead, we estimated the cost of a single day of our developers being non-productive, estimated the cost of putting up a new data center, understood that 2.5 days of non-productivity equals 1 data center, and build the data center. So now we have a data center where everything is being deployed just like it is on production system. Same topology. We have about 1/3 of the capacity, of course, but we have same topology, we have same data. We have anonymized samples of the data, which we copy from production to our early integration data center. We have same people who maintain our production boxes to maintain that data center. Basically, we have a NOC for development infrastructure, which also means that developers learn how to work with NOC early. And to make sure that we do not step on each other's toes, we also created that system to partition data so that everybody can create their own set of data users, just if they want to really modify something to change the interface from English to Japanese, for example, which is not something that you could do on a data that's shared. Not everybody reads Japanese fluently, not yet. So the effect is that before QEI, actually at the end of the quick deploy shared stacks, we got reports that about 20% of time was wasted, just wasted. You're trying to deploy something and you're waiting. Well, rumors are good, but we wanted to measure it, so we started to measure it. We instrumented our deployment procedure. We started to collect the data. We started to look at the graphs. And the truth was that the rumors were not exaggerated. About 20% of time was wasted. So now, imagine that suddenly you are 20% more effective. What would you do? And now I have to admit that I'm committing the worst sin of management. I'm ignoring people whatsoever, and I'm looking only at the numbers. But the point of this numerical exercise is to highlight how a simple increase in economy of development trickles down into big pile of time that we were wasting otherwise. So now we have more productive developers, which can produce more value, which means that for the given business directive, we can use less developers, which means that we don't have to spend time hiring, which means that we don't have to spend time interviewing and we don't have to spend time onboarding. But it gets better because when we have less people who can do more, they will have to collaborate less because they don't have to reinvent the culture every time, and they will communicate better. And we'll be able to raise expectations because once we know that something is better and it works, we can aspire to something even better than that. And then I think it's 1,800 openings that I found on LinkedIn with the word LinkedIn in that. I'm not sure whether we are really trying to hire 1,800 people, but I'm pretty sure that we do have about 1,000 of opening right now. In simple English, we are hiring. So becoming effective, hiring even more people, and bringing them into a culture of being effective. So the fact is that today, with 3 releases to production, we have been able repeatedly to push a service from conception to a first minimal viable product in production within 4 days. I would like to get it to 1 day. Right now, 4 days, which is which would seem absolutely incredible in 2010, which sucked. Okay. Now I'm going to get technical. But before that, any questions? Okay. Let me dive into the bits. So the overall scheme of how it works is described by this little diagram. We have that data center. We have all the pieces of data center deployed in data center, and we have a proxy that routes requests typically through the data center, but sometimes outside of data center into a local developer box. In order to keep track of different topologies, we use Zookeeper. And I hope that everybody read the Zookeeper paper, but if not, that it's not a requirement at all. We use Zookeeper, and we have created an administrator console where people can see and change the topology of their deployment. Which basically means that if I would like to deploy 3 services on my box, first of all, I can just deploy them, but then I can tell the system that they're actually not deployed on my box and then to turn them back again. I can share services that are deployed on my box with my colleagues. That's really, really, really handy in hack days. I have created this service, you have created that service. We'll just share our services, we'll continue working on that. Both of us will see the 2 services in collaboration, and after a few hours, we have a prototype, which is good. And we keep track of all the topologies in something that we call quick deploy profile, which is basically just a JSON document. The real magic, though, is happening outside of Zookeeper. The real magic is happening through our data center, and it's based on the fact that for every remote service invocation, we have something we call Invocation Context, which is basically a property bag that we put into a HTTP header, and we can put small tags into that invocation context. So what we did is, starting with the admin console, we are injecting a cookie into a browser. The moment the browser is making a request to our data center, we have a filter there that picks up the cookie with the name of the quick deploy profile and puts it into the invocation context. Starting from that point, every dependency, every fan out of this call will have that quick deploy cookie sitting on it, including the routing points that we were running into. So for legacy systems such as Spring RPC or all sorts of asynchronous communication, we use the centralized routing, which is an ATS box that knows how to route the request either to local machine or to HA proxy that sits right next to the ATS and knows how to route the request to the data center. We have separated the routing to the local machine from the routing inside data center so that our NOC can maintain the HA proxy in exactly the same way they would maintain it in production. As far as the routing back to the local machine, well, that's easy. That doesn't change. The machine name is always the address of that particular machine. For the modern services, though, we use distributed routing, which means that every service has an ability to announce itself, tell other services, hey, I'm here, I have those capabilities. You need those capabilities, you can call me. And we also have distributed load balancing capabilities built into the same connective tissue. So we instrumented that as well. And again, our distributed routing piece is examining the quick deploy profile, looks up the Zookeeper document, knows how to route the request to the local machine or to the main data center if needed. The framework doesn't stop on routing though, because we have 500 of developers and hopefully more, because as I said, we're hiring. And we have plenty of different technologies to support. So we're using a plugin architecture that allows us to create plugins in Python. We have a simple API, so that, for example, if I have non-standard deployment characteristics, we will be able to create a custom deployer, run it every time deployment is happening, and to completely customize the process that is happening behind the scenes. And then we've run into new challenges. People told us that they would like to modify database schemas on the early integration data center. And they asked for sudo. And we said, why? And they said, because they're going to change the database schemas on the early integration data center. And then we said, oh, oops. So obviously, changing database schema on a running data center is a tricky proposition at best, and a disaster at worst, and we don't necessarily know upfront which route it will take. So that was challenge number one. The second challenge was asynchronous data modification. If I'm putting a message into a queue, and then a few minutes later, it will be picked up, and it will trigger cache invalidation events, how the cache on the data center will remain coherent with the cache on the local machine? Won't we run into all sorts of incoherency? It turned out that we would, and we did. We totally did into cache incoherency problems. We also figured out that Zookeeper is painfully intolerant of high latencies, but also is able to generate high latencies of its own. So the latencies was the latest challenge that we've seen so far. So for DB schemas, we provisioned developers with virtual machine on Oracle and asked them to develop a schema modification locally. That circumvents triggers, that circumvents caching problems, because it brings the domain of data change fully to the local machine. So we are still working in that isolation of, I'm just a developer working on this Oracle virtual machine, but once the schema is somehow finalized or even brought to a milestone, we ship the schema to the data center, we update it there, and the developer can work in a fully distributed environment until next change to the schema should be brought in. So development of DB schemas is done locally. The testing is always done on the data center, because this is our golden standard of coherency. This is how we are going to ensure that whatever we're going to ship actually works, rather than, disillusioning ourselves. As far as asynchronous data modification, our primary approach is to separate the domain of modification and to have either all of the changes happen within the data center or within the local machine for a given data domain. And Zookeeper latencies, well, we just threw more hardware into it and built a dedicated Zookeeper cluster with updated tolerance to latencies. So far, it's working. Probably we'll get into new challenges. But so far, it's working. Any questions so far? Yeah.
So you use dedicated Zookeeper
So the question is whether we're using dedicated Zookeeper even for testing.
Like, presumably you need to spin up multiple testing environments. So does that mean you have a whole bunch of a whole tier of Zookeeper are bare metal, or?
So we use Zookeeper to communicate topology between the developer and the software that developer runs. So all testing environments, all the partition testing data is using the same Zookeeper cluster. However, we are running hundreds and almost thousands of Zookeeper profiles, and the distinction between different testing data sets is represented in those Zookeeper profiles. We have only one cluster though. Okay, so let me generalize a little bit. So first thing we changed is not to mess with things that we don't have to mess with. That whole business of deploying services that we didn't really know how to deal with and how to maintain and how to troubleshoot in case they would break, it was a huge waste of time. The second thing is to have people who know how to maintain, operate, and scale data centers to help us with maintaining, operating, and scaling data centers. So we're bringing the devs and ops closer to each other, and it has lots of benefits. First of all, developers learn to work with ops on a very early stages. So if, for example, monitoring is lacking, the developers will know about that very early. Instead of rushing to add some monitoring at 3 hours before going live, we're getting monitoring set up correctly, we're getting the runbooks written, we're getting the alerts set up, and developers learn how to talk to ops. We are building that DevOps thingy out of devs and ops, which used to be two different kingdoms. The third pattern that we are using is self-service. We used to open tickets for our ops guys to deploy services. Today, we have a system where we can mark a build as nominated for deployment. That build will be picked up within 15 minutes and deployed on the local data center. Integration tests will be run on the machine. If new failures will be given, developer will be notified. If no response happens within half an hour, we will mark this build for undeployment. The expectation, of course, is that people will nominate, deploy, and mark as healthy. So self-service deployment really scales the ability of people to write code. So we have removed another bottleneck by enabling self-service. And the last principle that I would like to highlight is that developing for development environment is a huge, huge fallacy. Because by optimizing code for development environment, we are pretending that we know what's going to happen, whereas we are not even close to knowing what is going to happen unless we try it in something which is close to real production environment. So the closer we get to the realities of distributed computing, and the earlier we do that, the better our software is getting. And that's about it. Except for, I would like to thank all of the folks who helped with creating that system. And I will be happy to answer your questions.
What's your repository structure for all of your services?
Please repeat.
How do you track the source control for each of the services? You say you're integrated to one main branch. Do you have a repository per service, or is it all in one big repo?
So the question is, how do we track source control for all different services? So we started with one big repo, and we were using different directories within that repo for different products. It worked well until a certain point. Then it stopped to scale because we had quite a bit of interdependencies within the directories. Besides, getting that big repo to be coherent proved to be a real problem. The integration tasks took longer and longer to run, and as a result of it, working with that big repo became a problem. Then we switched to a new model that we internally call multi-product, which creates a subrepo for every service. That subrepo can import modules, but in essence, every service is beginning to live in its own repository. So integration tests are faster, deployment is faster.
So you talk about how you've got these kind of partitioned environments for each engineer, and then they do their schema changes and things of that nature. It's such an integration environment, there's pass done and so forth. How do you maintain kind of data uniformity across all these different engineers? Do you replicate production data with maybe a scrubbing pass, or do you generate, simulate production type data, or is there a version data set? So how do you kind of address that issue with so many engineers?
Okay.
Framework?
So that's an excellent question, and the question is, how do we ensure data uniformity and integrity after we have partitioned the data? So we have, in fact, two different domains of data. First domain is anonymized subset of production data. We use that for our data-driven algorithms for machine learning and for anything that would benefit from a realistic, if not real, distribution of different pieces of data. It's impossible to do anything meaningful on simulated data. Therefore, we, every now and then, basically once a year, we take another snapshot of production data, we run it into a big pipeline of removing private identifiers, making sure that data will be anonymized, but still have the characteristics of real data, and add it to the address space of our data. In social network, a member ID is basically the primary key for everything. It may be enforced as a foreign key, it may be not enforced as a foreign key, but the member ID is the key, and the big bulk of our member ID address space is data that we have anonymized out of our production systems. However, for integration tests and anything that we would like to be highly predictable, using data that was originated by our users, modified and anonymized, but still originated by users, is not what we would like to do. We would like to ensure certain traits of data that we will be able to test our software against. So for that, we have a set of scripts that can get a unique member IDs. We're using Oracle sequences for the uniqueness. And based on the sequence of unique member IDs, we can generate a set of users, about 100 users. Each of them will have different characteristics. One of them will have connections of one type, the other one will have outstanding invitations, the third will have user interface in Japanese, etc., etc. We use that data for our integration tests, for our unit tests, and since that data is always very easy to regenerate, we do not attempt to preserve that generated data very much. So we generate it often, we remove it often. Any more questions?